So we are recording now. So I guess I'll be the one that has to watch what he says the most today.
Does it record the screen or all of us?
It records the screen and the audio. So what's projected right now will be recorded, and the audio. And I don't know if I'm far enough away or too far away. Maybe I'll try pointing it towards me. I don't know where the microphone is on this. I don't know if that's helping. I don't know. All right. But anyways, does anybody have any questions about anything? Because we're starting 2 minutes late. Although I did start 1 minute before when I asked you if it's okay. So don't go complain to the VCA just yet. So, anybody have any questions about anything? Okay. So this is where we left off in the notes. And we're talking about, now we're at it, we talked about before, about the salts. So, or I should say anions. If anions are weak base or pH neutral. And the only ones that are pH neutral are right here. So chloride, bromide, iodide, nitrate, perchlorate. And those are the conjugate bases of the strong acids. And I'm specifically also not bisulfate, because bisulfate is a weak acid. So basically everything else coming from an acid, the conjugate bases are going to be, in fact, basic when you throw them into solution. I'm sorry, the basic. Yeah, because why basic? Basic. Alkaline. Oh, I see. Basic, like ish. Okay, because they will rip a hydrogen off of water and then form hydroxide. Okay, so specifically though, if you mix these together, if you have a strong acid plus a strong base, you get a neutral salt. And strong bases are all the alkalis and alkaline earths. Everything else is a weak base. Strong acids, in this case, are HCl, HBr, HI, and nitric and perchloric, not sulfuric, because H bisulfate is a weak acid. So a weak acid and a strong base will make a basic salt. So back up, there's two definitions for the word salt. Okay, so one definition is a metal and a non-metal, the non-metal is not an oxide or a hydroxide. So that's one definition. The other one is a salt is the result of an acid-base neutralization reaction. So this is a better definition, is the salt is the acid-base neutralization reaction. And then a strong acid and a weak base gives an acidic salt, and a weak acid and a weak base, you don't know off the top of your head unless you know the values of Ka and Kb. So it depends, whichever value is bigger, Ka or Kb, will be the determinant. So the way I always remember this is that, strong acid, strong base, they cancel each other out. But then a weak acid and a strong base, the base is so strong, and it's not strong. It's stronger than the weak acid that the salt left over is stronger. That's not really what happens, but that's the way I always remembered it. But the reason why is that the conjugates of the acids and bases, the strong acid, strong bases, the conjugates do not react with water, but for the weak acid, weak bases, they do react with water. So that's the real reason why it works that way. So let's do this to determine some of these things. Determine if the salt is acid or base. So strontium chloride, this one here, this is a strong acid. So the Cl minus is from HCl, and strontium is an alkaline earth. That's a strong base. So this means it's going to be neutral. Does that make sense? Does anybody have any questions with this one? Okay, B, aluminum tribromide. So for this one here, we have a strong acid in the Br for HBr, and we have a weak base, because aluminum Aluminum hydroxide is not an alkali or an alkaline earth. So aluminum is regular old metal. So we have a strong acid and a weak base, and then that means that the salt is going to be acidic. So aluminum tribromide is going to be acidic. Questions with this one? Okay, so next one, we have methyl ammonia and methyl ammonium nitrate. So you have methyl ammonia here on the left and NO3 on the right. NO3 is from a strong acid, and methyl ammonia is a weak base. It's not listed on a, so I mean, the strong bases are only alkali metals and alkaline earths. So, based off of this is also going to be acidic. Making sense? Okay. Sodium formate is the next one. What color? Maybe green will show up. So sodium formate. Sodium is from sodium hydroxide. That's a strong base. Formic acid. This is a weak acid. And when you have a strong base and a weak acid, this forms an alkaline salt. So basic salt. So ammonium formate is a basic or alkaline salt. So what about the last one here? Ammonium fluoride. You have a weak acid and a weak base. This one, you have no idea. You have to look it up. In this case, it's actually acidic because KaHF is greater than Kb ammonia. But I mean, you wouldn't know that off the top of your head. That's not a really fair question on a test. Okay, but in this specific case, it is in fact acidic, but this is something you cannot tell just by inspection. So, make sense? Questions with this? Okay. How about potassium acetate then? So what do you think? So potassium acetate, is this salt acidic, neutral, or alkaline? How many people think this is acidic? How many think it's neutral? How many think it's alkaline? No one knows. Great. Okay. So potassium is what? Does that indicate it's a strong base or a strong acid? Or is that a strong base or a weak base? Why? Because it's an alkali metal?
Yes.
Yeah. Because
All zeros are
these two columns.
Oh, levels.
Strong base. Far left on the periodic table. Sorry to put here. So, the potassium indicates then this is a strong base. What about acetate? Is that from a strong acid or a weak acid? Do you remember the strong acids are? Strong acids, HCl, HBr, HI. What's that? It's a weak acid, yeah. This is a weak acid. The strong acids are so acetate is a weak acid. Or acetic acid is a weak acid, I should say. This is the salt from a strong base plus a weak acid. So how many people think this is acidic? How many people think this is neutral? How many think this is basic or alkaline? Okay, we have three votes for basic and 1 vote for acidic. The answer is basic. It is alkaline.
Strong base plus weak acid is,
Yeah, makes it alkaline. Correct. Strong base. The base is so strong that overcomes the weak acid, makes a alkaline salt. That's not really what happens. The potassium ion does absolutely nothing in water, but the acetate anion will rip a hydrogen off of water, H2O water, make OH minus. That's the real reason why. So, questions with this? Looks like some people got stuck. Did you need to have it explained again, or is there something that you don't understand? And no questions? If not, I'm going to move on. Okay. All right, so next topic is polyprotic acids. You've already seen one. We talked about it a bit. So sulfuric acid, battery acid, is well, the first one is strong. See, the Ka1 is strong. It's essentially infinity. So sulfuric acid has 2 hydrogens. Only the first one is strong. The second one is a weak acid, but it's still a pretty strong acid. As acids go, it's still pretty strong. So another one, oxalic acid. That's the stuff like in sweet potatoes and taro leaves. We also use it for oven cleaners. So like I've never done this, but has anyone ever eaten the leaves of an uncooked or taro plant?
you're not supposed to.
Yeah, why?
Because the crystals,
yep.
you know, like close up your areas.
Yep. Well, it's the oxalic acid. It'll poke them and they'll swell. They're pokey. So that's why you cook it, to break the crystals. So sulfurous acid. There's another one, 2 of them. Phosphoric acid. Citric acid has 3. Oh, phosphoric has 3. Citric acid has 3. Ascorbic acid, that's vitamin C, has 2. Carbonic acid has 2. I even drew one here in pink. This is EDTA, ethylene diamine tetraacetic acid. That's got 4 hydrogens. So you can even have 4 hydrogens. And EDTA is also a chelating agent. That means claw. So if you want to get rid of certain ions, specifically calcium, magnesium ions, you can use chelating agents. So you can use this to clean out pipes. The other thing is they put it in shampoo. So it'll chelate out calcium, magnesium ions so you don't get the white soap scum in your hair. Not a big deal for me because I have blonde hair, but for people with darker hair, you can get white soap scum on the hair. It doesn't look as good. So if you ever see EDTA, if you wonder why is EDTA in my shampoo, it's because to get rid of the soap scum. Okay, so let's use this to do a problem here. So pH of 0.01 molar sulfuric acid. So this is always a hard problem. So the way that you do this problem is a 2-step problem, and you really do 2 equilibriums. It's 2 equilibriums. The first thing that happens, you throw sulfuric acid in water, it just breaks apart very quickly into hydrogen ion and bisulfate. And then you have a second reaction where the bisulfate breaks apart partially. And so initially, you have 0.01 of this, 0, and this is a strong acid, so it goes all the way. It breaks apart completely. Equilibrium, we have no sulfuric acid, and we have 0.01 of this. So, does this make sense? So, this first reaction, it's just breaking apart completely. It's a strong acid. Strong acids are strong electrolytes. The reaction goes all the way to the right. So, is everyone? And there's no sulfuric acid left. It's all broken apart to form hydrogen and bisulfate. Is that good? Anybody have any questions on this? Okay. So then we have a second part where we have 0.01 of this, and we have a common ion here. The hydrogen is a common ion, 0. And since we have a 0 in the sulfate, we shift right. Then we have 0.01 minus x, 0.01 plus x, and x. And Ka, this is going to be products over reactants. We know it's and the problem with this one though is you can't disregard the x. It's too close. The 0.01 minus x, that's not insignificant. Remember when we had, if this was like times 10 to the minus 7 or something like that, you could disregard x. But you can't. So unfortunately, you have to do the entire quadratic equation. So you have to solve for x directly. And so we can start by multiplying by 0.01 minus x. So we have 0.012 times the quantity 0.01 minus x equals x times 0.01 plus x, which equals 0.01 x plus x squared, and then 0.00012 minus 0.012x. So, sorry, let me make this prettier. So now we have to get all of them on one side. So we have to add 0.012x and subtract 0.00012, and we get 0 equals x squared plus 0.022x minus 0.00012. Am I doing that right so far? Looks right. So then apply the quadratic equation written there. X equals minus b minus 0.022 plus or minus the square root of b squared, 0.022 minus 4 times a, actually it's going to be, it's plus that because a is negative. 0, I should say c is negative, I'm sorry. A is 1, 0.00012, all over 2a. Okay. All right, so also looking at this, it's not going to be minus because the x has to be positive because the x, among other things, is the concentration of sulfate. So that number has to be positive. So the plus root is the only one that's going to work. So let me put this in my calculator. Are you following my logic for determining the root there? Yes, no, maybe? Questions so far? I'm getting some confused faces. Okay, minus 0.022 plus the square root of 0.022 plus 4 times 0.123 divided by 2. Okay. I'm getting something that's probably a little too big. Oh my God. Oh, I didn't square B. That's what I didn't do wrong. Sorry. B squared minus 0.022 plus the square root of 0.022. And x equals 0.0045. That's a 4. Okay. And so we want pH, so the hydrogen ion concentration is 0.01 plus x equals 0.01 plus 0.0045 equals 0.0145. And then pH minus log hydrogen equals minus log 145 1.8. Okay. Oh, this problem's always hard. Okay. Multiple step problem. All right, let me do a recap real fast. So, diprotic acid, sulfuric acid. And the way you do these problems, a two-step problem. And the first step for sulfuric acid is it breaks apart completely. Second step, you have to, and then take the values from the first step and put them in. And the difficulty is, difficulty number 1, you have a common ion. Hydrogen ion's common. And this equilibrium, the second equilibrium shift right. And then you get those values there. And Ka2, products over reactants, 0.012 equals x times the quantity, 0.01 plus x. And the 0.01 plus x is the hydrogen. And then 0.0 divided by quantity, 0.01 minus x, that's the bisulfate ion. And you FOIL it, write it out in the form ax squared plus bx plus c equals 0, and then apply the quadratic equation. Just knowing that you need to have a positive answer, the negative root gets discounted, the positive root's the only one that's included. and you get x equals 0.0045 for that value. And then hydrogen ion, back up to the chart, right here, the hydrogen, right here, the hydrogen ion. The equilibrium value is 0.01 plus x. So then the equilibrium concentration is 0.0145 molar. And then the pH is minus log of the hydrogen ion concentration, which is 1.84. Do you follow that? Questions on how to do that? Okay. So the nice thing is that you pretty much only have to worry about doing the whole equilibrium for that for sulfuric acid. The other weak acids, for the most part, don't really matter. There's a question on the midterm with a weak acid in it, the next midterm, and you only have to worry about the first one. I'll show you in the whatever you want, the problem session before the test that you can discount it, the second hydrogens, because usually you can discount the second, third, and fourth hydrogens when it comes to pH and concentrations. So, and the only one you have to really worry about is sulfuric acid, and specifically dilute solutions of sulfuric acid. So, questions? Okay. So, next we have a philosophical question. Why do acids act like acid? Well, it's the bond strength. So when you look at molecules, when I look at this molecule, so if you can peer inside my brain, what I see in this molecule, I see for perchloric here, you have electrons around all of these, of course, electrons around the hydrogen. And what's happening is, so the most electronegative atom is fluorine, and the second most electronegative atom is oxygen. So what happens is that the electrons get pulled this way, and they kind of go around a little bit with chlorine, but the oxygens, they really, they're just like electron vacuum cleaners. They're sucking a lot of electron density away from the hydrogen, and the reason why this is a strong acid is it's real easy to break this bond right there. That hydrogen sticking onto the oxygen is just really weakly bound, and it can easily pop off. And if you look as we go down, as we have fewer oxygens, so this is the top one is perchloric acid. Chloric acid, it's a pretty strong acid. Chlorous acid down here, that's still pretty strong. And hypochlorous acid, it's a fairly weak acid. So when you look at the other way, start at the bottom with hypochlorous acid, HCl low. If you add another hydrogen, so this hydrogen here, it's pretty bonded. It likes to stay together. So add another oxygen to it, electron density gets pulled away from the hydrogen, weakens this bond, but it's still holding on. Another oxygen weakens it even more, so this is a fairly weak bond. And then when you add the fourth oxygen, it just completely weakens that bond. It can pop off very easily. So, which means that an acid, and what makes something acidic is actually a weakly bonded hydrogen, among other things. So, at least for the Bronsted-Lowry definition of an acid. And you can learn about this in organic chemistry. There's certain hydrogens called acidic hydrogens. So here's methanol here. And methanol has an acidic hydrogen. It has the one attached to the OH. So this is an acidic hydrogen. These are not. The ones attached to the carbon are not acidic. This is an acidic hydrogen. So you can actually, so in water though, this is not going to break apart in water. But you can take methanol or ethanol, and you can throw sodium metal or potassium metal into it. It'll form the ethoxy ion for ethanol, or, I'm sorry, methoxy ion for methanol, ethoxy for ethyl alcohol. And those are very strong bases. So if you ever want to have a stronger base than hydroxide, you can use the alcohols. And the hydrogen in the OH group in alcohol is considered to be an acidic hydrogen. So, and this idea, which proton is more acidic? It's going to be the one on the left, number A, because it has more oxygens. The oxygens act as they pull electron density. These oxygens here, they pull electrons away from the hydrogen, making it weaker. This oxygen does pull electron density away from the hydrogen, but the other oxygens pull much more, making chlorous acid there a fairly decently strong acid. So, and making sense? Questions so far? Okay, so what really happens though, I know I've been talking a lot about I mean, in terms of proton donor, proton acceptor, what about Lewis theory? So why does HCl break apart? What happens is that the electron density from the water, the base in this reaction, is donated to, remember, so Lewis acid and bases, the acid is an electron acceptor, base is an electron donor. So here, water is donating electron density to hydrochloric acid, and hydrochloric acid has a bonding orbital, anti-bonding orbital. The electron density gets added to the anti-bonding orbital. The hydrogen ion pops off, and then it goes and attaches itself to the water, making H3O+. So that is how it really happens, is actually a transfer of electrons. Not necessarily, I mean, it's a transfer of proton, but it's a transfer of electrons. So there are certain types of reactions called Lewis acids and base reactions. And in this case here, you can see aluminum trichloride reacting with ammonia, and the electron density is going to move there. You can form this molecule here. This happens in the gas phase, and you have this trichloroaluminum single bonded with ammonia. And other reactions, you can get boron trichloride reacting with diethyl ether, and you can form another molecule here. So in this case, just like the trichloro aluminum, the trichlorobromide is acting like a Lewis acid electron acceptor. So, okay. So that's how you can also, you can define all acids and bases as Lewis acids and bases, but there are certain reactions that happen under unique circumstances that you can only classify as Lewis acid and base reactions. These two reactions are some of them. So, questions so far? This is a little bit more advanced. This is not necessarily going to be on the test. So, questions with Lewis acids and bases? No questions. Okay. Good, moving on. I need to warn people that have moved in, we are recording this lecture. It's going to be posted to YouTube later. So, if you don't want your voice recorded, don't talk. Okay.
I love YouTube.
So does anybody know what you should do for ethylene glycol poisoning if you are not near a hospital? So what do you do if you're in the Australian outback? Let's say you're halfway between Hana and Kahului, and you don't have a car, and you accidentally drink antifreeze. Do you know what you're supposed to do? Fair enough. Or, okay, let's do the Australian outback. Say you're in the Australian outback. Your car breaks down and you accidentally drink antifreeze. What are you supposed to do? The answer is get rip-roaring drunk. So, yeah. One of the cures for ethylene glycol poisoning is alcohol. Another one is methanol poisoning. Another cure for that is ingestion of alcohol. So ethylene glycol poisoning, what happens is that our body oxidizes it and it forms glycolic acid, which causes your blood pH to drop. and then people die from that. And humans tend not to die from this as frequently because we are pretty good patients, like patients for doctors. And we usually say, "Oh, I drank antifreeze. It tasted sweet, but now I feel funny." Like, "Oh, okay, quick, let's get you some alcohol and maybe inject you with some baking soda, some sodium bicarbonate to even out your blood." So that's probably what they would do in the ER. So, of course, if your cat goes and drinks it, your cat's not going to come and tell you, "I just looked up it's this green-looking liquid in the garage floor, and now I'm panting." That's the last step with acidosis. Usually, the animal starts to hyperventilate as a way to increase the pH of the blood. So, but it usually doesn't work for glycolic acid. You can't hyperventilate enough to even out the pH. So what happens, among other things, is that it also causes your oxygen carrying capacity to go down. So if you look at this equilibrium expression, hemoglobin plus oxygen, having too much hydrogen will then shift left, and then the oxygen will not attach to hemoglobin as well. So with that regards, blood has to really closely regulate its pH. And we have a way of doing that. It's called a buffer. So a buffer is something that, so here's a buffer characteristic, resists a pH change. And this is for acidic one. A buffer contains a large amount of a weak acid and its conjugate base, or if it's in a more alkaline buffer, it could be a weak base and its conjugate acid. But most cases it's a weak acid conjugate base. Or it can be a polyprotic acid, so phosphoric acid can also be used as a basic or alkaline buffer. And how this works, if there's a weak acid and strong base together, if acid is added to the solution, the base will react and destroy the acid. If a base is added to the solution, the acid will react with the base and neutralize it. So that's how the buffer works. And here's a picture of a buffer here. So you have a weak acid conjugate base, so acetic acid, and then sodium acetate. That's the salt of a conjugate base. So remember that, it's a strong base and weak acid, so that's an alkaline salt. Mixing them together gives a buffer solution. And there's a really nice and easy way of solving these. It's the Henderson-Hasselbalch equation. The pH equals the pKa plus the log of the base over the acid. So this is one of the most important concepts of this class, this equation right here. I guess you guys are not going to go on and take organic. Are you guys going to go on and take other biological classes like micro, or this is it, huh? Oh, so someone is going for micro. A lot of biology classes use this, so no one's going to take any more biology classes, huh? Okay. What? You are? Okay. So some of you. So, man, I guess this is a terminal class for a lot of people. Oh, anyway. But, so you'll see this equation again and again and again, especially in bio classes. You don't necessarily have to, so the top one is base concentration over concentration base, concentration of acid. You can get rid of, so concentration is moles per liter. So you can get rid of the liters on both, and you can have moles of base over moles of acid. That works fine too. Sometimes it's easier to do it that way. But if you look at sorry, I should zoom back. So if you look at the equation, you'll see this used quite frequently. So the next question is, which one's the base and which one's the acid? The acid is the one that has the extra H in it. Okay, that's the first hint. The second hint for the base usually has, it's going to have an alkali, almost always an alkali, like sodium or potassium. Lithium isn't used as frequently, because most of the time these are used for biological things, and lithium has a biological effect, specifically for mood stabilization. So lithium ions can affect you a little bit ways. So especially a lithium carbonate, that's the manic depressive drug that was used for a while. So typically the base has either sodium or potassium in it. The acid has the extra H. So let's do this for a problem. Calculate the pH of a buffer solution that is 0.05 molar in benzoic acid and 0.150 molar in sodium benzoate. Benzoic acid, the Ka is 6.5 times 10 to the minus 5. So there's written as the Henderson-Hasselbalch equation. So what is the pKa? The pKa is equal to the minus log of the Ka, which is minus log 6.5 times 10 to the minus 5. You can even include it. Actually, I don't even have to calculate it. I can just put this in the equation. So pH equals pKa, which is minus log 6.5. Yeah, ugly. 6.5 times 10 to the minus 5 plus the log of the base concentration. So which one's the base? It's the one that has a sodium in front of it. So 0.15 divided by the acid. Which one's the acid? It's the one with the extra H in it, benzoic acid. So 0.15 over 0.05, that's 3. So 15 over 5 is 3. So minus log of 6.5 e minus 5 plus the log of 3. This equals 4. So we have 2 sig figs. 4.66. And it's that easy. So you can do an equilibrium. You don't have to use the Henderson-Hasselbalch equation. You can write out the sodium benzoate. So you can say hydrogen plus benzoate equilibrium with benzoate. Oh, actually, no, I guess it's the other way. How would you do this? Plus hydrogen ion. So this is going to be, you're going to have this be 0.05, 0.150, we shift right, so we lose x plus x plus x, so 0.05 minus x, 0.15 plus x, and then do the acid, the Ka. The Ka is going to be the hydrogen ion, benzoate anion over that, and then solve it all out, disregard the x's and the other thing. That looks like that's a lot of work. I mean, you can do it that way, or you can just throw it right in an equation, and you get an answer pretty quick. So, and also the Henderson-Hasselbalch equation, it has the discounting x inside of it. So the derivation of this includes the discount x stage. So usually students are excited. You look so excited, guys. But this is much easier. So students tend to do very well with buffers.
Yes.
Right? So one equation, pretty easy to use. All I gotta do is put in the pKa, put in the base and the acid, and out pops the pH. So real simple for this one. And the most common question asked among the students is, which one's the base, which one's the acid? The base is usually one that has sodium or potassium in it, or it has the alkali, it's sodium and potassium. The acid has the extra H. Okay, so if you remember one of those two things, you will probably be fine. Yeah, probably. Okay. So let's see if you can solve this one. Quarter molar hydrogen cyanide and 0.17 molar potassium cyanide. pKa is 9.31. What's the pH? So which one's the base? KCN, yeah, potassium cyanide. And the acid, it has the extra H, the hydrogen side. Is anyone getting stuck? Raise your hand if you're getting stuck. Some think it's A. I think it's B. I think it's C. All right. C is the correct answer. So I'm assuming then that no one needs any additional explanation of this. Isn't this easy? This is great.
I like this stuff.
Yeah. The catch is you have to know the other stuff before this.
That just makes it seem like a real problem. It's like super hard.
Okay. So I'm going to talk a little bit about titration curves. You're probably about here in the lab, aren't you? Or what are you guys doing in the lab now? Le Chatelier? Yeah. Okay. So this is a titration curve. It's known as a logistics curve because the y-axis is a logarithm plot. Okay, so there's certain types of functions. So not logistics like how am I going to move my couch out of my living room to my new house. Not that kind of logistics. I mean, logistics is in logarithm. So pH is a logarithmic scale. So this is a logistics plot. And if you have titration of a strong base and a strong acid, so initial pH, so if you can see here, down here in this part right here, this is a pH of 1. So that's about 0.1 molar or something like hydrochloric acid. And then you start to add milliliters of base, and it creeps up slowly. Then you get this huge jump, and then there's an asymptote then as you add more and more base, it asymptotically approaches the concentration of the base that you're adding. So if you're adding 0.1 mole, if you start with 0.1 molar hydrochloric acid, titrating with 0.1 molar sodium hydroxide, there's an asymptote on the top that it'll approach towards the pH of 13, which is 0.1 molar sodium hydroxide. So a couple things to note with this graph. There's a funny point here, and also the equivalence point. So this equivalence point right here, that's when the moles of acid equals the moles of base. How many of you have had calculus? Do you know what a second derivative is? Raise your hand if you do not know what I'm talking about. Okay, so some people, okay. The first derivative is the slope of the line. Second derivative is called concavity. So you might notice that there's something also where I'm marking there on the graph. There's a change in concavity. It's going from here. This is known as concave up, and then this part is called concave down. So you see where the graph kind of points up towards the sky on the left, and on the right it kind of points down. This point right here, that is known as an inflection point. It's also where the second derivative hits 0. So when computers do titrations, one of the things that they do is they calculate out the second derivative, or it hits 0. That's where the equivalency point is. So you have what are called the inflection points there for that graph. So there's a lot of information in these graphs if you look closely. And let's look at the opposite. Here we have a strong base and a strong acid. So there's a titration here. And starting off with a solution of strong base, it's just like the same way as a strong acid, but it's opposite. So it starts going down, 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 then has this big kick, and then it asymptotically approaches the whatever concentration acid you put in. And there's also an equivalency point, and notice it's right at 7. So it was the same thing for the strong acid, strong base. So remember that the salts, so the equivalency point, it's right at 7. So the equivalency point for a strong acid, strong base is 7, and this equivalency point is also an inflection point, because there's concave down here and concave up. Do you see that, where the function kind of has a certain kind of, it kind of cups a certain way. Concave down means it cups down. Concave up means it cups up. So that's the inflection point. Okay, so now here is a weak acid and a strong base. So a couple things to note about this. Notice the pH is a little higher. It starts a little higher. It doesn't start here at 1. It's starting at like 2 something, or maybe even high as 3 or 4 for a weaker acid. And you have initial jump up, then it kind of flattens out. I mean, it's still going up, but it's not shooting up. There's this flat area here, then it jumps up, and then it flattens out at the top. So some things to note. There's an inflection point here. It goes from concave down to concave up, and then we have another inflection point here. So there's a couple inflection points. So this one right here, I'm writing with an X, that's the equivalency point. That's where the moles acid equals the moles base. And also, pH is 7, so a weak base and a strong acid, that's going to have an alkaline salt. So the equivalency point is above 7. And also, this inflection point right here has something else. This also equals the pKa. So this this middle inflection point right here, this also equals the pKa. And so this is one way you can get a rough estimate for the pKa of a weak acid, is you can do a titration, and then you can look at the graph and where the inflection point is. And it's about here. You can just kind of eyeball it. It's about right there. And so the pKa of this one is going to be like 3.8, 3.7. So you can get, I mean, it'll be, if you do it much more carefully and get it, you'll get a much better value for the Ka and then take the minus log of that. But you can look at the graph and you can get a kind of a good estimate from right here. So, and this is also the buffer zone. So this part right here is the buffer zone, which means that's the usable part of the buffer. So this buffer zone is good from about 3.5 to 4.2. Or actually, no, it's about 3. So like 3 to, so from a pH of a little bit above 3, and it could be 3.5. It's hard to tell exactly there. Maybe a little bit less, 3.2 to 4.25 or something. So that's the buffer zone. So this wouldn't work for a pH of 5. So a pH of 5 would be right here, and then if you add base to that, it'll jump up. So buffer only works for a certain zone, for a certain combination of strong acid and weak base. Okay, so let's do the other way around. Let's have a weak base and a strong acid. And it's just like the other one, like with the weak acid and the strong base. There's this initial downturn. You have a buffer zone here in blue, and then you have so this is concave up, this is concave down. You have another inflection point. That inflection point is also going to be the equivalent of the pKb for that base. So this pKb is going to be a little bit above 9 for this base. So the Kb is going to be something around 10 to the minus 9-ish. And then equivalency point, so here's 7. 7 is right here. Notice that the equivalency point is below 7. So weak base plus strong acid gives you an acidic salt. So the equivalency point, the salt, the salt-only solution is acidic. So which we learned before. So, and then what about polyprotics? So many protons. Many protons here we have. So this one is actually H2SO3. So, and can you see that? I'm having a hard time seeing that screen. Is that too weak for you? Raise your hand if you're having a hard time seeing that. Oh, you see it fine. Okay. All right. So this one here, like the weak acids, you have the initial jump up. Then you have a buffer zone. There's an equivalency point. And then there's another buffer zone. There's an equivalency point that goes on. So this first equivalency point is where you have just HSO3 minus. And the second equivalency point, this is where you have SO3 minus 2. But one of the differences is, of course, you have an inflection point here, 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 and here, because this is concave down, concave up, concave down, concave up, concave down. And you're going to have the pKa1 there, pKa2 there. And so what I'm trying to get at is that if you look at these graphs, you can actually get a fair bit of information from them. Do you have a question?
Does this determine the rate of reaction?
No. No, this is, you mean for like kinetics?
Each, like, slide actions, this is like,
I don't. I mean, I'm not exactly sure what your question is saying, but for reaction order, that's kinetics. And the no, it would not. This is just. It tells you, the more information it tells you, it'll give you an estimation of what the equilibrium constants would be before the inflection points are. The other information you can get from it is the usable buffer zones. So the usable buffer zone is going to be about right there and about right there for that one. So you know where you can, so this one would be good for a pH of about 7, a higher 7 pH, and also a pH of not quite 2 at like 1.7. So, and the human body, I didn't talk about our buffer system. We use carbonic acid, H2CO3, and sodium bicarbonate, which is also known as baking soda. So if we, under certain conditions, if you have acidosis, one of the things they will do is they will inject you with solution of baking soda. So, I'm sorry, any other questions? Okay. So, we're done with that one. It's always amazing how fast this goes once we get through a certain point. And there is, we have time to go through. I can get through that easily in one day. Let me mention this real fast, and we can probably get out of here a little early. Some metal hydroxide. I know I'm changing topics, but and this is also not on the test. So, but I mentioned this kind of before, that metal hydroxides, or metals can form complexes, but metal hydroxides can act as acids and bases. Actually, maybe I should return back to that later. Sorry, I shouldn't jump ahead so far. I'll talk about that next class. But we're at a good stopping point, I think. So where are we? Okay, so anything else? No. Okay, so yeah, but I'm glad you guys like the buffers. Students usually really like the buffer stuff. It's so easy. So I should say it's straightforward. It's a better word to say. And let me reiterate that this Henderson-Hasselbalch equation, it has the discount x included in it. So if you want to do the equilibrium and then solve a quadratic, you will get a different answer than the Henderson-Hasselbalch equation because this equation discounts the x. So, all right. Does anybody have any questions? All right. Well, in that case, you get 11 minutes of your life back. So, I will try posting this to YouTube. See if it works.